Hello all, welcome to next tutorial. This tutorial is called Simple Abstract Model. So this is the content. The objective of this tutorial is to author a simple abstract model in a analyst way. So welcome to abstract model authoring role. All previous tutorials have introduced you to the various abstract model building blocks, CAENexus GUI and various features. Although you might still feel how do I start setting up a new model. So this tutorial and next two tutorials, that is basic menu to one and versatile menu to one, will focus more on the concrete step, that is how to start authoring. So this abstract model is called one-to-one abstract model. So why we call one-to-one abstract model? We are going to assign only one abstract class to one component. Hence, we call it as one-to-one abstract model. So abstract model schematic. With this tutorial, we depart from our approach to click dictated steps and we start to think like a CAE analyst. Our objective in this tutorial is to understand the physics or problem statement and relate this with abstract methodology. Hence, there will be some description instead of instructions. Let's take two product geometries. So this one is Y tube and this one is Y duct model. So if you try to write a problem statement applicable to both models, what it will be? The simplest possible would be fluid enters the domain through the inlet and exits through outlets. So this is first problem statement. Next is properties of fluid, that is like air, water. Next, inlet boundary condition and outlet boundary conditions. And the most important one is we want to generate CAE simulations on our model with efficient, robust, consistent method and with least human interruption. So this is the problem statement. Now let's try to interpret these points from the problem statement. So let's interpret first point. So there is one fluid and there is one inlet and there is one outlet. The word abstract can be described as it exists in thought or as an idea but not having physical or concrete existence. So accordingly, let's choose our abstract class as fluid, inlet 2D and outlet underscore 2D. To represent our physics, here suffix underscore 2D is just convenient notation to separate 3D class from 2D class. Note that the notation for abstract class is represented by rectangle in the following image. Please take a note of double-sided arrows connecting inlet 2D and fluid class, which represents a relation. So it means the fluid class and inlet 2D are connected and is a part of our problem physics that we defined above. Similarly, fluid and outlet 2D class are connected and will represent a relation 2. There is one more relation in this image, that is the relation between fluid and fluid class represented by two-sided curved arrow. Just for understanding purpose, let's take help of this schematic. So fluid class is attached on all four parts, that is inlet pipe, connecting pipe, outlet pipe 2 and outlet pipe 1. So when we say fluid-fluid relation, so it evaluates the common phase between inlet pipe and connecting pipe, the common phase between connector pipe and outlet pipe 2 and connector pipe and outlet pipe 1. Hence, in abstract way, the fluid class is connected to itself. The point 3 and 4 of the problem statement state about behavior of our abstract entities, for example class or relations or closures during final simulation, which we call as attributes. Abstract model attributes. The attributes can be either mesh requirements, physics like boundary condition, material, etc. or post-processing behaviors. So look at the image below, which defines the schematic relation of the attributes and their specification on abstract entities. That is either class or relation or closure. So here we can see that on relation of fluid and inlet 2D class, we have put a monitor, let's say pressure monitor. Then here on this relation we have specified the inlet boundary condition, then it is a physics. Then on fluid relation we have specified this non-physical boundary condition. Then on fluid class, let's say we have defined a mesh size attribute, then element set attribute, or let's say volume monitors are specified, or a wall boundary condition is specified, or we want to generate a boundary layer, so we have specified the boundary layer attribute on boundary of fluid class. So similarly, we have specified one monitor attribute on relation of fluid class and outlet 2D class, and we have defined the outlet boundary condition. So these many attributes are defined on abstract entity. Apart from the attributes on individual geometric entities, we may need some on complete model. We may also need some attributes which may not at all be related to geometry. Look at the schematic image below, which illustrates some simple attributes like mesh curvature attribute for meshing, then material model in physics, and then length scale factor again in physics. So these attributes are defined on model or global class, which are not related to geometry. Since we have our product description as well as schematic abstract model, let's try and author the abstract model. Have a look at our product description and schematic of our abstract model below. So there are two inlets having mass flow rate of 0.1 kg per second, and one outlet is having pressure outlet boundary condition with 0 Pascal. There are four parts like in a tube, inlet tube 1, inlet tube 2, connector tube, and outlet tube 1. So here we have attached fluid class on each part, and we have defined inlet underscore 2D class on these two surfaces and outlet underscore 2D class on this surface. So there will be an inlet boundary condition with mass flux of 0.1 kg per second. Then there will be a pressure monitor on this relation between fluid and inlet 2D class. Then a non-physical attribute on fluid relation, that is these three common phases. Then there is outlet boundary condition of on relation of fluid and outlet 2D class. Then there will be a mesh size attribute on fluid class, then element set attribute on fluid class. Then there will be some monitors, then wall boundary condition on boundary of fluid, and on boundary of fluid we will define the boundary layer attribute to generate the boundary layers. Next, on global or model class, we define mesh curvature, material model, and length scale factor. So this is the schematic of abstract model. So let's start authoring an abstract model from scratch. So scratch folder for this tutorial is located at CAENexus installation directory, help, tutorial, CFD, basic, and tutorial number 12, simple abstract model. Create a folder at suitable location and copy the CAD data from scratch folder and open it in CAD software. So I am setting working directory and opening YTube assembly. So I am using already tagged CAD model. So here you can see the fluid class is attached on all 4 parts, and also here in tools, parameters, then surfaces, if you select this surface, you can see that this outlet 2D and inlet 2D, and this surface is again inlet 2D. So these surface tags and volume tags are attached. Now start the CAENexus with appropriate CAD modeler. So I am choosing Creo 7 and Messim as measure and Accusol 17 as my solver. So this is CAENexus window. So first set the working directory. So I am setting the working directory. Now save as this blank abstract model. So we have saved this blank abstract model file. Now through action import from CAD, import the CAD model. So we can see that as per our schematic diagram, the fluid class is imported and it is attached on all 4 parts, and this inlet underscore 2D and outlet underscore 2D classes are also imported, and it is attached on respective surfaces. Now create the necessary relations. So first relation is fluid relation, next is fluid and an inlet 2D relation, and last one is fluid and outlet 2D relation. So switch to meshing tab and create the required attributes for meshing. So select the model class through create, then mesh curvature and this relative mesh size of 0.04. Again select model class, create minimum mesh curvature, that is we specify as 0.5 mm. Now select this fluid class and specify a mesh size attribute. Let's say the mesh size of 6 mm. Okay, now select this boundary inside and create a boundary layer attribute. Let's say specific height and specify some boundary layer heights. So let's say first layer as 0.1, next is 0.12, next is 0.5. I am randomly specifying it, but you can use a specific growth rate and generate the boundary layers. So next one is 1 mm, last one is 2 mm. Okay, so I am creating total 7 boundary layers. Also, we want to skip the boundary layers from inlet and outlet surfaces. So select this relation and create boundary 3D and select this no boundary layer attribute. So I have created no boundary layer attribute. So similarly select this relation of fluid and outlet 2D class and boundary 3D no boundary layers. So these attributes are created inside the meshing tab. So now switch to solution strategy tab. So these attributes are independent of geometry. So select global, then analysis. It is a static analysis. Okay. Now select this equation. This is specified in equation. I am selecting a Spalart-Alamas turbulence model and everything, keeping it by default. Next, create this auto solution strategy and this initial time increment of 1 e raised to 10, then minimum and max time increment is same, convergence criteria, then number of iterations. I am like specifying it to 50, number of time steps, max number of time steps. So remaining I am keeping as by default. Okay. So now switching to problem definition tab. As per our schematic of this problem, so there is an inlet boundary condition, outlet boundary condition, then element set, then wall boundary condition, and there are some monitors and material specification and length scale factor. So let's create those attributes. So select the model class and create a length scale factor. So as our model is in mm, so specify the length scale factor as 0.001 in all the direction. Next, select this inlet, select this relation fluid inlet underscore 2D and create the simple boundary condition of inflow, and instead of velocity specify it as a mass flux and specify the value as 0.1 kg per second. So similarly select this fluid underscore outlet 2D relation and create outlet boundary condition. So outlet outflow boundary condition and our pressure value is 0. Now select the fluid boundary inside and create a wall boundary condition. So this is our default wall. Next, select the global class and create a material model. Okay, so this is full material model. So material type is fluid and I'm specifying the fluid air properties. You can name it as matte air. Viscosity, let's say 1.789 into e raised to minus 5. Now select this fluid class and create a cell zone attribute. So or element set attribute. So I have created this and selecting the material model that we have created. Everything remaining is by default. Let's say is cell zone air. So similarly, like you can rename other attributes like inflow. This is inflow. Next is outflow, and the last one is wall. Now on fluid-fluid relation, create a non-physical boundary condition. So the required attributes are created. Now switch to output tab. Now let's create some monitors. Let's say fluid underscore inlet 2D relation, and I am specifying the surface output attribute. Let's say so underscore inflow, and similarly on fluid underscore outlet 2D relation, I am specifying another surface monitor as SO underscore outflow. Now save the AMF. So now create the simulation model. In simulation model, check that the attributes are correctly transferred or not. So the first we check in class tab. So on fluid boundary inside, we have specified the boundary layer attribute. Next, we have specified no boundary layer attribute on inlet, on relation of fluid and inlet 2D, and also on relation of fluid and outlet 2D. So we have specified the mesh size attribute on fluid class, and we have also defined this mesh curvature and minimum curvature attributes. So similarly, we have specified this element set attribute on the fluid class. So now check in model tab. So first check the mesh size attributes. So there are 4 difference on which fluid class was attached. So here the 4 attributes are created, and the mesh size is 6 mm is specified. Similarly, on this face uses or faces, the boundary layer attributes are created, and this surfaces where we have skipped the boundary layers. So now in element set, we can see that the 4 attributes are created, as there are 4 different regions. There are 2 surfaces on which inflow boundary faces on which the inflow boundary condition is defined, and this is the outlet surface on which the outflow boundary condition is defined. So the attributes are correctly transferred. Now click on mesh model, so it will mesh it. Once mesh gets completed, just export the job and run the AccuSolve job. So mesh is completed. So now export the job. So I am naming the export as export underscore 1 and exporting the AccuSolve job. Export is completed and it is exported in this folder. So you can run this job in AccuSolve and check the results. Now have a look at our product description and schematic of our abstract model below. So this is our second model. So this is viaduct model. So there is one inlet, there are 4 parts having fluid class and 2 outlets. So this is the schematic of this viaduct model. So inlet 2 underscore 2D class, fluid class, and outlet underscore 2D class. And there are different attributes created. Now open this viaduct model in appropriate CAD software. So I am opening the viaduct CAD model. So here in this model, the fluid class is already attached on 4 parts, and also the surface component tags are also attached. For example, let's say on this surface inlet underscore 2D class is attached. Now switch to CAENexus window. Now open the already set up AMF file. So this one-to-one accusol underscore 12 abstract model that we have set up previously is open. Now import this viaduct CAD model. So everything is blue as these classes are already present in abstract model file, and all the attributes are already we have already created. Now just create a simulation model. Next, mesh it and export the job. Let's say I am exporting this job into export underscore 2. So export is completed. Now check the export and run the simulation. You can check the results. We hope you enjoy the simple abstract model for viaduct model. As you might have already realized, we created an abstract model once for Y-tube, and for viaduct we just reuse the abstract model. Moreover, you achieve this automation without writing a single line of code or script. So as an expertise CFD professional, your answers to following questions could illustrate level of abstraction using classes. How many problems in CFD would not have fluid or solid? How much percentage of CFD problems would not have inlet underscore 2D or outlet underscore 2D? How many times we need to monitor field variables at interior surfaces, that is are fluid or inlet or outlets? Finally, the current tutorial one-to-one does not really explain the most efficient way to start authoring the abstract model. In next session, we will have glimpse of how it can be made more generic and hence more efficient. Later, we will do the next tutorials and we will understand how abstract modeling enhances automation capabilities and is reusable across different workflows. Let's do little more addition to our simple abstract model that we just authored, and look at our product description and schematic below, which is added with rotating moving reference frame, that is MRFA, rotate A class to our abstract model. So this is the geometry of moving reference frame. The boundary conditions like total pressure inlet, then pressure outlet boundary condition, and the rotation speed is 100 radian per second. So here an additional class of rotate A. You can see the schematic here: inlet underscore 2D, fluid class, outlet underscore 2D, and rotate A class. So again there is one inlet, one outlet, and these are again some common attributes. So now we will try to set up this problem using current one-to-one abstract model. So open the MRF model And here you can see that on this rotor an additional class of rotate A is attached. Rotate A is attached. Now fire the CAENexus. So this is the CAENexus window. Now open the already set up or authored abstract model file. Now import the CAD. Notice here that the rotate A class is imported as a new, and we can see that there is a red cross mark. So this is newly added class. So save as this AMF as 1-to-1 Accusol to 12_1. Now change the mass flux inlet boundary condition to pressure inlet boundary condition. Now on global class, create the reference frame attribute, specify the center of the rotating fluid, then specify the axis of rotation and its rotating speed in radian per second. Now on rotate A class, create a element set boundary condition. I am selecting the material and select this newly created reference frame and name it as cell zone rotating. Now select rotate A boundary inside and create a simple boundary condition of wall and select this reference frame attribute and name this wall as rotating wall. So these are the changes required to modify this AMF for this forced convection. Now save the AMF and create the simulation model. So here you will see that there is an attribute conflict at two places. So this fluid class is attached on all four parts, and also we are trying to create a rotate A cell zone, rotating cell zone on this rotate A class. So there is a conflict. So increase the precedence of required attribute. So I am increasing the precedence of cell zone rotating, and here also there is a conflict, so I am increasing the precedence. Now save the AMF and again create the simulation model. So in simulation model, let's try to find out whether our attributes are correctly transferred or not. So I'm directly going to model tab, and in model tab we are checking the element set volume attribute, and on region 2, that is a rotating region, the cell zone attribute is transferred correctly, and all remaining 3 parts or components, the air cell zone attribute is transferred. So we can also check that these are the rotating walls, the attribute is correctly transferred. So now there are 3 simple steps, like mesh the model. So mesh is completed. Now export the job. So I am creating a folder, export_. MRF. And exporting the job. So after completion of export, so run this simulation and check the results. Export is completed. So with simple efforts, we have reused the already set up abstract model for this problem. So if you face any difficulty, you can use the already set up AMF and tagged CAD models from done folder. So thank you for watching this tutorial. See you in the next one.